everyone. I'm going to try to record a bit of what I was supposed to cover today, and I'm really sorry that the Zoom function seemed to be not working. I'm going to log on much earlier on Tuesday so that I can have everything ready to go. The person who is the support person at Fullerton College thought that maybe it was just a problem with tons of people trying to use Zoom at once, and that the system was overloaded. So if I can get on early and if everybody can get on early, I think that we should be okay. So I'm going to make sure I'm on by at least 8:20, but maybe 8:15 in the future. And so anyway, I'm sorry, but let's do the best we can. You all saw that I did manage to talk to some of the students using a Microsoft function. If we have trouble using Zoom in the future, I will send you a link for that so that we can just pick up and use that as well, because it does seem to be a good backup. Now, you know, we've been talking about visual processing, and we spent some time talking about the what and where pathways. Of course, you know, primary visual cortex is back here in V1, and then the action potentials do spread as they go forward. And as they go forward, they tend to spread along two main pathways. Some of them, of course, some of the action potentials go this way, but of course, you know, this is the dorsal stream, so this is up towards the parietal lobe, and then this is the ventral stream down below. The ventral stream is called the what pathway. And one aspect of the what pathway is something you can't see very well on here, but if I could pull out a little bit more, this brain, on the inside of the temporal lobe, you would see the fusiform gyrus. On this figure right here, you actually can see the fusiform gyrus pretty nicely. And I'm going to highlight it a little bit in yellow. That is not working very well. And I guess I'm going to have to erase it when I'm done. But that is the fusiform gyrus. And of course, you have a left and you have a right fusiform gyrus. Now, the right side of the brain is over here right now because of the fact that the brain is upside down, and so if it would be flipped over, reversed and flipped, the right side is going to be what is now on your left side. But it's the right fusiform gyrus in particular that helps you to identify faces. So a mnemonic for that is you can think that the fusiform gyrus fuses together complex features, because of course a face is a complex image. I'm drawing a face for you right now, and I'm going to make it a happy face. And to be able to know which face you're looking at, you have to fuse together lots of details. Of course, people can identify others by the hat that they wear, hair color, things like that. And if you look at a test for facial processing, what they do is they put the face in an oval so that you can't actually see the hat. This YouTube link right here talks about prosopagnosia, which is the name for facial blindness. So you definitely need to know that word, prosopagnosia. My mother, as I've mentioned to you, had prosopagnosia. I did talk to you about this coyote here, and this was as a way to introduce the concept of motion to you, and that we can see motion as a result of how our brain strings together images. So here, the part of the brain that helps us to identify motion is area MT, but it's also known as V5. And so you can think of it as MT as a motion middle temporal lobe, but it's also known as V5, and that if a person has damage to that area, and they have to have bilateral damage, so on both sides to that area, they can be rendered with the inability to detect motion. So I did talk to you all previously on the video about the woman who couldn't cross the street. That's why I have an image here of people crossing the street. We take for granted that we can track something moving towards us, but imagine if your brain was only taking snapshots and it was like an apparition in Harry Potter. It goes bleep, and then bleep, something like that. I'm going to move on. Now, one thing that I did start to talk to you all about, but I didn't spend a lot of time talking about, was how early development plays a role in shaping what we can see. People quite often want to try to understand what a newborn can see, and so they spend time looking at what's called the fixation time. Now, of course, this is just a brain that I have in my hand, But a newborn can't talk, can't say, oh, that's an interesting face, and oh, that's beautiful, I really like it. But a newborn can tell you what it's interested in by looking at it and staring at something. They can use eye tracking technology, and there's so many really cool studies of eye tracking technology. I was talking to my husband's son about a study just yesterday that has been done on individuals who have autism, and one thing they find, and there's a ton of incidental learning that they miss out on socially because they're not focused on the face, and the face gives you the most amount of information usually when it comes to people and what's happening. Of course, we talked about some cultures can mask their expressions, but what's interesting is that for eye tracking data will show that young children, if they do have autism, they're focused on something else, like an inanimate object. Well, most children, though, are going to focus on the face. And what's interesting is that studies show that infants, and even though you can't see this slide here, you all can open it up when you're looking at it on your PowerPoint. On your PDF. It's not showing now because of the way I'm recording this. I just learned how to do this. Another thing, yay, Guthrie is learning, that I learned how to do. And so in order for you to be able to see my video at all, it obliterates the words. And I didn't have the time to rearrange it because I'm back behind schedule with so many things. But I just wanted to give you all some video to make up for what we lost today. But anyway, on this slide, what it shows beneath the graph is that it says infants show a strong preference for a right-sided up face. So for a face that's turned up, they can show infants lots of other figures, but the infants will stare more, stare longer at a face. And even though it says that their ability to perceive faces usually kicks in at about 2 days, you don't have to worry so much about that, but just know very early on infants are processing faces. Now, this slide is very important. I mentioned this to you on the previous lecture, even though I didn't have a slide, but I was telling everybody that the brain actually has to learn to perceive the world that you're in. And so think about it. This wonderful brain comes to the world with so much potential. And of course, we've talked about neuroplasticity. We know that the young brain has more neurons than an older brain. The thought is that this young brain has more neurons so that it can become specialized. And then at some point, synaptic pruning will occur, especially we know in the prefrontal cortex, but in other areas of the brain too. So if these areas, these pathways are not really used, locked in, those synapses will decrease. Now the other neurons, the axons of the neurons will become more fully myelinated, so the brain becomes even more efficient at working. Now, some research that shows that early development can change the way that we perceive the world is research done on kittens, unfortunately. And I'm sorry, there are a lot of cat lovers in the house, I know, and I really do like cats too, so it's kind of hard to hear. But this kitten that you see on the image here has goggles on it. So they can do a ton of things with this, where they can keep the kitten in goggles from the time that it's born, so literally it only sees the world through horizontal lines. They can, of course, do it so that it only sees vertical lines. And when they take the goggles off, like after several months, which for a human being would be equivalent to about a year or so, that kitten does not seem to perceive straight lines if it has not seen them previously, if it's only seen vertical lines, and vice versa for if the goggles were the other way. So that's one thing. Now, another thing that they can do in some of these studies is as soon as the kitten is born, they will stitch the eye closed. One thing I was talking about with everybody today in lecture is that I had a crossed eye, and that's somewhat equivalent to like stitching the eye closed if that eye crosses very often, because the brain will stop processing through the eye. So one thing we know, that if the kitten has the eye stitched closed from a very early age, or somebody has problems seeing from their eye, like if they have a cataract, the other eye becomes dominant. I'm left eye dominant, even though most people who are right-handed are right eye dominant, right foot dominant, but I am not right eye dominant because my right eye does not work very well, because for a lot of my life it was not really processing images. I can see out of it, it's just not as clear as it should be. Now, so notice on the slide it says, now you can't see this, but if you look at the PDF, it says early lack of stimulation of both eyes can create more sluggish responses, but it does not render an organism, in this case a kitten, blind. But if one eye is shut, like so for me when I talked about the one eye that didn't work well, the other eye starts to become dominant. One thing that you'll see on the next slide here is what's called ocular dominance columns. Now you don't really need to know the word ocular dominance columns per se, but if you notice, if you trace the lines, the occipital cortex actually gets input, and so what they've done is in this slide is they've taken occipital cortex and stretched it out. But the occipital cortex, it gets input from both eyes. So what I want you to think about is if one eye is not working or sutured closed, that eye doesn't have an opportunity to strengthen the axons that would go to the contralateral hemisphere. I shouldn't have started drawing that line up there. So the contralateral hemisphere, in this case, if this is the right eye, is going to be the left hemisphere. Now, this eye, because it's closed, no longer has an opportunity to input, to have synaptic connections to this part of the cortex. So in a sense, it's losing its territory over time, because what happens with the other eye, and that would be the left eye in this case, is that the left eye is able to strengthen its connections, and as it strengthens its connections, it's like it competes and it starts to take over the cortical space, because the brain really doesn't leave cortex unused. So it's like two siblings. If you have two siblings and one sibling is a weaker sibling and doesn't have an opportunity to kind of vie for its space in the car, maybe it's younger, the other one will take over. But if there's no other sibling there, they can't take over. So what I want you to understand is that the eyes have to compete for their space in these columns in the occipital lobe, okay? And there are a lot of studies that show this. You don't have to read the article, but this is just one link here. Now going on to the next one here, this is something that I was mentioning to you early, and nature can create experiments in a sense for human beings. With the cats, you can just suture, take the eyelid and shut it early on in life. But in a human being, you can't do that. So you have to look for, in a sense, a natural experiment. A natural experiment would be for human beings that are born with cataracts, either in two eyes or one eye. If they're born with cataracts in two eyes and those cataracts are removed very early, now see, you may not really know, but a cataract is when the lens, so remember we talked about the lens, when the lens is cloudy. And people can be born with this problem. And people, unfortunately, can develop cataracts as they age. The lens becomes damaged by UV light, by the sun, basically. And that's why it's important for people to wear sunglasses. I don't. I'll probably have cataracts and have to have my lenses replaced. Now, people can have their lenses replaced. They just cut into the cornea. And of course, this is different from LASIK surgery, where they cut into the cornea and shave off part of the cornea. But they can cut into the cornea and they can actually insert, I'm going to cough, sorry. Excuse me, they can insert a new lens. My father was he was 90, 92 when he passed away. I'm the last of 7, so my parents were much older. They've been gone for a while now. But my father had artificial lenses for years, which is fascinating. Now, the lenses don't accommodate, like most of us. Mine are getting more rigid over time because of my age, but most of us, when we bring something close, our lens actually pops. So it's like we've got a flexible window inside our eyes that's clear, but people who have cataracts, it's cloudy. Now, in the United States and in a lot of places in the world, if a baby is born with cataracts, they actually will do surgery very early on so that the occipital cortex has a chance to be developed. But if people have cataracts and they're not corrected, say until they're like 20 years of age, so they're really blind. They're blind because the eyes, of course, cannot process. Remember, you can be blind for numerous reasons. You can have the occipital cortex be damaged, and that's, of course, what happens with blind sight. Remember, with blind sight, the people have to have their eyes working. Because remember, the subcortical parts of the brain can actually process visual images. But we're talking about when people are legally blind because the eyes are not working because of cataracts. These individuals, when those cataracts are removed at a later period in time, they could not see very well. And that's because the cortical area in the occipital cortex does not develop. So notice it says that vision can be restored after early deprivation. Deprivation in this case means not being able to see. Sorry, I was trying to underline that. Especially if it's before 6 months of age. So there's this window of opportunity for the occipital cortex to develop well, to be strengthened, but after that it can decrease. Now, one other thing I want to show you on this slide here, on this set of lectures, and I should have actually imported the auditory lectures with here, so I'm going to have to stop it and start another one. Goodness gracious. So this is actually showing what's called retinopathy or retinal damage. Now, you don't need to know retinopathy per se for the exam, but I do want you to understand what retinopathy is, okay? So when people have damage to their retina because of blood vessel changes like high blood pressure and other things, they actually will start to have these spots occur. And there are some interesting studies that have been done that have looked at people over time. Like, let's say if you have a person who's in their 40s and they start to have these spots in the retina, what they've realized is that these people are going to be more likely to have cognitive changes as they age. And what scientists have determined is that in the retina is very sensitive to blood vessel changes because it has these tiny, tiny capillaries, these really, really little blood vessels. So remember when we talked about stroke and ischemic stroke, we talked about how blood vessels can become clogged. And of course, if you have a blood vessel that's of a smaller diameter, it's more likely to be clogged. People who have retinopathy, they're actually having blood vessel changes, and because the eyes have all these tiny little sensitive blood vessels, they're losing retinal tissue. Their photoreceptors are dying. So these bright spots occur because somebody will take, a optometrist will take a flashlight and they flash it in the eye, or they have some other device as machines now, and they dilate the eye so that the pupil, so that the pupil doesn't close, because normally if you flash a flashlight, remember we talked about how the brainstem does this automatically, and both pupils should respond the same. After a head injury, if one pupil is a little sluggish, you know that's a bad sign because it usually means there's been some brainstem damage or maybe some swelling that's causing the brainstem not to work as well. But if you flash the light into the eye with the pupil dilated, what happens is if there's been tissue damage in the retina, the light bounces back off the back surface. So that's why you see these bright spots. Now, the reason you see this bright spot right here in the middle is because that is the optic nerve. The optic nerve does not have photoreceptors over it, so that's normal. But what is not normal are all these other bright spots, because those are spots that are showing up because the retina has been damaged. It's really kind of unfortunately sad, but it's also kind of cool if you think about it. So in this sense, the eye really is kind of a window into the brain, not a window into the soul per se, but a window into what can happen with the brain, because they realize now that these small blood vessel changes also are probably happening in the brain, happening elsewhere.